Send her the hardcover as a gift, and hope that you'll take it into her side.
Hello everyone, this is Mech here, and in this video you will learn how to create a mesh with the block mesh utility in OpenFOAM. Here you can see the finished results, some exemplary results of the velocity magnitude, the temperature and the pressure. I have to tell you that this case is a very unphysical case, but it is good enough because here we want to learn how to use block mesh. And here you see the created meshes, a uniform mesh, and then I will show you how to refine your mesh. The goals of this tutorial are the following. I want you to understand the block mesh dictionary, how you define the coordinates of the vertices of the geometry, how you define blocks, how you can set the refinement of your mesh, how you can define boundaries, and how you execute the command. And I want to also simulate 10 seconds of a flow around the forward step and post-process the results, but really I want to concentrate on block mesh in this tutorial. For the simulations we will use the Sonic Foam solver. The official description is that it is a transient solver for transonic, supersonic, laminar or turbulent flows of a compressible gas. So this means that the solver is compressible, it is transient, it can both describe laminar and turbulent flows, it is a single phase solver, and it is a non-isothermal solver. I do not want to go into the theory here because I want to really concentrate on block mesh, so let's just jump into the simulations or into block mesh. I will open up a Nautilus here. And as I mentioned in the first tutorial, my installation is in my home, OpenFOAM. So check where your installation is and then go into the tutorial folder. Now compressible and Sonic Foam, laminar and forward step. But as I mentioned before, it is a good idea to have one base case and then make a copy of this base case and then do the simulations in the copied folder. I will do that in the terminal. I will open up the terminal by pressing Ctrl Alt and T. I have to navigate into the appropriate folder by typing CD space and then OP, and you can fill in the rest of the folder name by pressing Tab. Again OP, Tab, and then tutorials, compressible, Sonic Foam, and laminar. Enter. I type in ls and list the folders. And now we copy this forward step into the same folder. We make a copy of it by typing cp space -r forward step and forward step _1, and what this will do is it will copy the case into the another case, and which we call forward step _1, and I press now enter. If I type ls, then here you can see that there is now forward step _1. If I enter forward step _1, then you see that here is the usual case setup with 0, constant and system. I go back and I want to jump into block mesh. The dictionary for block mesh is in the constant folder and in polymesh. If you remember, in the first tutorial we used a mesh file and we imported the mesh information from that file. We will not do that here. We will execute the block mesh command, and for the block mesh command you need a dictionary, and I open up this dictionary and I want to tell you what you will find in this dictionary. You always find a header and then several entries like convertometers, vertices, blocks, edges, boundary and merge patch pairs, and I want to concentrate on some of them here. that we will need for this tutorial. For example, convert to meters. 1 means that the values that you defined under vertices are given in meters. If I would type here in 0.001, then these values would be in millimeters, and BlockMesh would automatically convert them to meters. But I want to give them in meters, and now I want to explain you the entries here under vertices, blocks, and so on. For that, I will go further here. Here you see the entries: convert to meters, vertices, blocks, edges, boundaries, and merge patch pairs. And I want to concentrate on these 4 entries now. These are the entries that we need for this tutorial. So, I explained what convert to meters means. Now let's go to vertices. Here you see I just copied the vertices from here to this presentation. Here you see 4, 8, 12, 16 vertices, 16 coordinates of 16 vertices, and I want to explain those, what those mean. Here you see the coordinate system, the x and the y direction, and I will show you here a schematic sketch of your geometry. The first 8 vertices have a z coordinate of minus 0.05, and then the second 8 have a z coordinate of 0.05. So I will concentrate on the first 8 and then show you the rest of the coordinates. The first coordinate number 0 has an x and y coordinate of 0, so I place it here. Then the second coordinate has an x coordinate of 0.6 and a y coordinate of 0, so it's shifted a little further in the x direction. Then coordinate number 2 has an x coordinate of 0 and a y coordinate of 0.2, so it's shifted in the y direction. Coordinate number 3 has an x coordinate of 0.6 and a y coordinate of 0.2, so it's here. Coordinate number 4 has an x coordinate of 3 and a y coordinate of 0.2, so it's located here. Vertex number 5 has an x coordinate of 0 and a y coordinate of 1, so it's up here. Coordinate number 6 has an x coordinate of 0.6 and a y coordinate of 1, so it's here. And coordinate number 7 has an x coordinate of 3 and a y coordinate of 1, so it's here. And the rest of the coordinates have the same x and y coordinates as the coordinates up here, so it's 0, 0 and 0.60 and further on, but only the z coordinate is different, so those are shifted in the z direction. This is what the geometry looks like, and now I want to show you how you build up blocks. If I jump back to the dictionary, these are the vertices, and then you define blocks. So you define 3 blocks, and you do that like this. I will show you the 2-dimensional representation of the geometry instead of this, because here you have a lot of vertices and you will not see anything. Keep in mind that the geometry looks like this, but I will show you the 2-dimensional representation. The first hex is made up by these 8 numbers, which represent the coordinates with these values. So the first block is made up by vertex number 0, 1, 3, 2. So it's 0, 1, 3, 2, and 8, 9, 10, and 8, 9, 11, and 10. So it's 0, 1, 3, and 2, and 8, 9, 11, and 10. The second block is made up by the vertices 2, 3, 6, and 5, and in the by the other four vertices with 10, 11, 14, and 13. And the third block is made up by the vertices 3, 4, 7, and 6, and 11, 12, 15, and 14. Now take care of the orientation of the vertices. It's 0, 1, 3, and 2, and not 0, 2, 3, and 1. So take care of the orientation, this is important. And it is the same orientation in all the blocks. So it's 0, 1, 3, and 2, and then again the same counterclockwise orientation 2, 3, 6, and 5, and 3, 4, 7, and 6. Now for the mesh itself, these vertices are not the coordinates of your mesh, but rather the coordinates of your geometry. But now we come to the mesh. You define the mesh within these brackets. And here in the first block we want to place 25 cells in the x direction and 10 cells in the y direction. In the second block we want to place 25 in the x direction. It has to be the same number here, and 40 in the y direction. Then in the third we want to place 100 in the x direction and 40 in the y direction. And also these values have to match. In the z direction we will place one cell because we want to make a two-dimensional simulation. Now for the boundaries, for that I will jump here into the block mesh dict. I skipped the edges because we do not need this for this tutorial, but I will come to that a little bit later. So for the boundaries, we define here 1, 2, 3, 4, 5 boundaries. The inlet, the outlet, bottom and top, and the obstacle. And you define boundaries like, for example, the outlet as a type patch, and then with a face or several faces. For example, the obstacle, the inlet and the outlet are patch. The obstacle should really be wall, so I will save that like that, as you will see later. But let's just check what this means. The outlet is made up by this face, 4, 7, 15, and 12. And I show you here the entire geometry. So the outlet is made up by 4, 7, 15, and 12. 4, 7, 15, and 12. And the orientation is very important here because this defines the normal vector of your face. I show you here the normal vector, and how you remember the correct orientation. I pulled up here a picture which I found on Google, so I do not take credit for this picture. You can find it here. So if you think of the magnetic field around a wire, then you can find the orientation of the magnetic field with the right hand rule. If you stretch your thumb and you curl your other fingers and your thumb shows in the direction of your current, then your other fingers will show you the orientation of the magnetic field. You can use this exact right hand rule for the orientation of your vertices here. If you stretch your thumb in the right direction for the outlet now, then and you curl your fingers, then your fingers will show you the correct orientation 4, 7, 15, and 12 for the outlet boundary. Now for the inlet boundary, the normal vector should always point outwards of the geometry, out of the geometry. So if you point now for the inlet your thumb to the left hand side and you go, for example, to this face, then your fingers will show you a direction of 0, 8, 10 and 2 for this face here, and 2, 10, 13 and 5 for the face up here. And this is the correct orientation. And the same is true for the other faces. You can try it out. So then you have to point your thumb to the top or to the bottom. But here we define a boundary called bottom, a boundary called top, and a boundary called obstacle. And bottom and top are both symmetry planes. And I will show you them here with this yellow boundary here and here. And the obstacle is shown by this gray boundary. So the symmetry planes means, I will show you this here with this two-dimensional representation. The symmetry planes are here in the top and the bottom. This means that you can mirror your geometry along this symmetry plane to the top and the bottom. What you end up with, here is your geometry that we define here with the inlet and the outlet, and you can mirror that to the top and to the bottom, and then you can continue on mirroring it further on, and what you end up with is a set of semi-infinite long plates with a certain gap in between them, with an inlet here and outlets here, and you investigate the flow, the two-dimensional flow in between them. Now let's just go to the simulation itself. 0, we use these vertices, this refinement and this number of cells. I will just type in block mesh and this will create the mesh. Here you see in constant polymesh we only have 2 files, and now if I execute block mesh, now we have additional files. I want to open up the boundary file here, and now you see that there is an inlet, an outlet, a bottom, a top, an obstacle, and an additional boundary called default faces, which has a type empty. And since we did not specify all the faces, so we did not specify here the front and the back plane, block mesh will automatically collect them together into one boundary and set them to be empty, because in the Z direction we defined only one cell. And here you see the symmetry plane, and the obstacle is a wall, and the inlet and the outlet are patches. Good. Before I start the simulation, I want to show you at first the grid. I open up it in ParaView. I showed you in the last tutorial how to open up an OpenFOAM case. You can do it with the VTK format and with the control dict, but there is a very simple way to do that. You just create a dummy file with the extension .foam. So I will just create this a text file by opening up a dummy file called, let's just call it foam.foam, or I can just call it forward step.foam. I could type here in whatever I want. I won't do that. I just save it with Ctrl O and exit. Now I have this file forward step.foam, and if I type in ParaView space forward step.foam and press enter, now ParaView will automatically know that I have an OpenFOAM file with this extension .foam. Let's just wait until ParaView opens up. Okay, we are here. I press apply. And this is what the geometry looks like. Surface with edges. And here you see the mesh. It's a rather uniform mesh. Here you see the blocks, block number 1, block number 2 here, and block number 3 here. And if I go back to our block mesh dictionary, we define in the first block, for example, 10 cells in the y direction. And indeed, if I count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cells. Here, you can believe me, these are 25 cells, these are 40 cells here, and these are 100 cells. And in the Z direction, we only have one cell, and we want to make a two-dimensional simulation. These are the front and back planes. Default faces here. The inlet is on this side, the outlet is on the opposite side here, then bottom is here, top is here, and obstacle is here. So it works. Good. So I will show you the internal mesh again, like this. Good. Now we could start the simulation, but at first I want to quickly show you the initial conditions. Here you have P, T and U. We also have a temperature because we have a compressible solver here. I open up P, which is the pressure now, really the pressure with the dimensions of Pascal. We initialize the pressure to be 1 Pascal in the entire geometry. We fix the inlet pressure to 1, and you have a fancy boundary condition on the outlet, but do not be concerned with that. And you have to specify symmetry plane on the bottom and top, because these are specified to be symmetry planes also in the mesh. And then on the obstacle, the pressure has a von Neumann boundary condition, and the default faces are empty. Let's just open up the temperature T. Here you see that the dimension is Kelvin, so there is no kilogram, no meter, no second, and the fourth entry here within the SI units is the Kelvin. These three are mole, candela and ampere, but in most of the OpenFOAM simulations you will not use these values here. The four important units are kilogram, meters, second and Kelvin. So the temperature is set to be 1 Kelvin, and this shows you that this case is a very unphysical case, but it is good enough because we want to learn here block mesh. The inlet temperature is set to be 1, the outlet is 0 gradient again for Neumann, and symmetry plane, 0 gradient on the obstacle and empty on the default faces. Now for the velocity is initialized with 3 meters per second in the positive x direction. Three on the inlet, then the outlet is 0 gradient and symmetry plane, and on the obstacle we have the no slip boundary condition. This is why I changed here the obstacle to be wall, because the obstacle is really a wall. And I want to show you these two dictionaries in constant turbulence properties. The flow is laminar, so it's set to be laminar here. And in the thermophysical properties, you can really set the thermophysical properties like the specific heat or the viscosity or the Prandtl number of your fluid. So I want to show you additionally the system folders, the system folder and the control dict, the FV schemes and the FV solutions. In the control dict, we define the controls for the simulation. We say that we will start from start time, which is 0, which is good enough, and we will stop at end time, which is 10. We will use a delta t of 0.002, and in the first tutorial we defined the right control to be time step. So we said that every 20 time step we want to save, or every 40 time step. Now we define the write control to be runtime, and in this case we do not define the number of iterations, but rather the time when we want to save. So we want to save after 0.5 seconds, after 1 second, 1.5 seconds, 2 seconds, until 10 seconds. In these steps. FV schemes, we will not change the interpolation schemes, we will leave it as it is. And also in FV solutions, we will leave the matrix solvers as they are, and also the residuals, and the number of inner and outer loops also. So now we will just start the simulation here by typing in sonic foam. I press enter, and this will take a while, so I will stop recording now and come back when the simulation stops. Okay, so the simulation stopped after 10 seconds. Now let's just take a look at the results in ParaView, and there is this very handy button called refresh, because if we would just go now to U and go to the next frame, then nothing really would happen because we did not load the results yet. So I go back to 0. Now if I click refresh, then I have access to the results of in the saved OpenFOAM solvers. Oh, I mean OpenFOAM folders, I'm sorry. ls, now you see that there are the results, and I can zoom in, and this is what the results look like. Velocity, and depending on your OpenFOAM version, these results might be a little bit different, but do not be concerned with that. So this is the velocity, this is the temperature, this is the pressure. I go back to the velocity, and let's just say that we find that the resolution here is not good enough and we want to change that. How do you do that with BlockMesh? If I go back to here to BlockMesh and take a look, let's just change the resolution here. And now I come to this simple grading part. Simple grading means the difference in the refinement in the beginning and the end of your block. And here it's 1 in the X, 1 in the Y, and 1 in the Z direction. So this is why we have this uniform mesh. Now if we want to have a refined mesh here, a finer mesh here, and a coarser mesh here, then we have to type in here 0.5, and the same in the second block, because we want to have the same refinement here and here. I just save this, and now I will delete the results because we do not need them, and you can type in for that rm, remove, space -r. You need -r because we are deleting folders and not only files. I delete them, press the middle mouse button, this will paste everything that I selected, and I press enter, type in ls, now they are gone. And now I re-execute BlockMesh, and this will automatically overwrite the mesh files in constant polymesh. Press enter. Now I go back to ParaView and I go back to 0. Press refresh. Nothing happens. I have to reload this, and now you see that here you have a finer mesh than here. Now how can you control which side you can refine? And this is defined by the direction of your edges. and the direction of your edges are defined like this. I will jump with that to the user guide. So open up your user guide. You will find the user guide in OpenFOAM and then in doc. So go there and open it up on page 138, and here the block mesh utility is defined, and here is such an exemplary block, and the direction is defined by your vertex number 0 and the edges which originate from this vertex. So all the edges in the x direction will have the same direction as your edge originating from 0. So this is for the edge between 0 and 1, vertex number 0 and 1, so this direction. Then in this x2 direction, so this will be the y direction, all the edges will have the same direction, which is defined by 0 and 3. And in the x3, so this is the z direction, all the edges, also curved, possibly curved edges, will have the direction like this edge from 0 to 4. So this means for our case here that vertex number 0 is here, and in the x direction we have this edge is going from 0 to 1. I jump back maybe here, so from 0 to 1, this edge is defining all the direction of all the edges that are looking in the x direction. So the direction is always this way, in the positive x direction, and the refinement is always defined, as you will find also in the user guide. The expansion ratio is the end width of your cell divided by the starting width of your cell. So we specified 0.5, so this length divided by this length gives 0.5. If you want to have it the other way around, we just type in, no, here in the block mesh dictionary we type in 2 and 2, save. I re-execute block mesh, refresh, and now we have the refinement on the other side. Now you can always think about the orientation, or like I do most of the time, and most people I know do it all the time. I just try 0.5, and if it's the wrong orientation, then I just change it to 2. So this is the primitive way of changing it. For example, I can also change the y direction here to 0.5 and re-execute block mesh, refresh. And now you see here we have a finer mesh here than here. And here grid is rather coarse, so I can change also the number of cells. For example, in the x direction to 50 and in the y direction to 20. So let's just do that. 50, I have to change it also here to match, and 20. Block mesh, and now refresh. And now we have a nice refinement here. We could do the same here along this edge, but now I want to show you something else. I want to show you another alternative to simple grading, namely edge grading. And with simple grading you can only define the refinement in one direction. So the refinement is the same for all 4 edges within a given block. So 4, for example, in the y direction 1, 2 and 3, and then here you have the fourth edge, and the refinement is the same for all four, but with edge grading you can explicitly define the refinement for each edge. And I will just copy this edge grading here, copy, and I will paste it here into my block mesh dictionary, and I will uncomment this first line. You can uncomment by putting in slashes, and I will just copy this to here and delete simple grading and use edge grading in the Z direction. So these are the 4 edges in the Z direction in the first block, but we really need here 1 because we only have one cell in the Z direction, and so this would correspond to a simple grading of 1 and 1, 2 and 1. Now let's just check what we would have here. So we have 1, so uniform grading in the X direction, and a grading of 2, so we will have a fine mesh in the bottom and a coarse mesh in the top. But I also have to change, of course, this value here. And now I execute block mesh and I refresh, surface with edges, and now you see that really this is what we have. So a uniform grading in the X direction and a refinement here in the bottom and a coarser mesh up here. So with this you can change individual edges. And if I now go back to block mesh and for example change here one value to 0.5, so on one edge the refinement will be the exact opposite. Refresh, and here is the same, but as you see on this edge the refinement is inverted. And this does not make sense for a 2-dimensional mesh, but for a 3-dimensional mesh it might make sense. Okay, now I jump back to the user guide because there are 2 entries that I did not explain, edges and merge patch pairs, because we do not need this for this tutorial. But with edges you can define curved edges with splines, for example, if you need curved edges. So take a look at the user guide. And also with merge patch pairs you can merge overlapping patches like you see it here. Good. So what did we learn in this tutorial? I showed you how to use the block mesh dictionary and how to execute the block mesh utility. I explained you what convertometers means, how to define the vertices of your geometry, then how to build up blocks, how to define the number of cells within a given block, how to control the refinement of your mesh in a given block, and how to define the boundaries here. Now this concludes this tutorial. I hope you enjoyed it and that you learned something. I thank you for watching, and I hope to see you next time.